So here's a relative velocity problem that is just a modification of the previous one, where this time the boat's trying to cross the same river, but it wants to get across in as short a time as possible. And the question is, how long will it take to get across, and how far downstream will it land? So in this scenario, the boat is going to point straight across. So here's the velocity of the boat with respect to the river, and we were told in the previous problem that this is 15 meters per second. So it sort of puts all of its effort going straight across like that. But now the boat, in addition to motoring across like that, will be dragged downstream, so it will have a vector like this with respect to the Earth. Velocity of the boat with respect to the Earth, so that it will go this way, and it will wind up down here somewhere. Starts here, winds up down there. And so one of the questions is, how far does it wind up downstream? And the other question is, how long will it take to get across? So the first thing that we're supposed to do is list our variables, and we've done that. They're sitting here in the picture. Now we want to put those variables into the equation. So I have the velocity of the boat with respect to the river is equal to the velocity of the boat with respect to the Earth minus the velocity of the river with respect to the Earth. And so I want to plug in to this. Velocity of the boat relative to the river, it's going straight across, so that's all in the y direction. 0 in the x and 15 in the y. And now the velocity of the boat that's angling across, we don't really have any information about that yet, so I'll list it as two components. The velocity of the boat relative to the Earth, x, velocity of the boat relative to the Earth, y. And then that's minus the velocity of the river with respect to the Earth. That's all in the x direction, 10 and then 0. So we write the two equations for this. Say the x direction equation. That's 0 equals VBEX minus 10. And we can immediately see that VBEX is 10. And the y direction, 15 equals VBEY minus 0. And again, we quickly see that VBEY equals 15. Oops, miswrote this one up here. VBEX should be 10. Okay, so there are the two components. They're both positive, and per our picture, that makes sense. So if I want to find out how long it takes to get across the river, then I want the component of the boat's velocity going across the river. In other words, the vector I just found, let me draw it here. This is VBE, the full vector. I want the component of that that's going across. So here's the component going down the river. Here's the component going across the river. They were 10 and 15. And perhaps you already knew that logically from the original setup of the problem, that the boat had these two components going down the river at 10 and going across the river at 15. But now we just sort of let the math push us in that direction anyway, if you didn't already realize that. But maybe right off the bat you could have already drawn this triangle. And so now if we want to get the time to go across, that's using this velocity of 15 meters per second. So I'm going to do kinematics with that. So this is in the y direction. So the kinematics in the y direction, delta y, v naught y, by, a, and t. Now the acceleration going across is 0. It's a constant velocity. And that constant velocity is 15. So it's 15 both places there. And then getting across is 800. And we're trying to find the time. So the kinematic equation to use here would be delta y equals v naught yt plus 1/2 at squared, where the acceleration is 0. So it simplifies to just the delta y equals velocity times time. And sometimes when people work a problem, they want to go ahead and jump to this equation. This is only valid because the acceleration is 0. So don't just automatically write, another way to write this, speed equals distance divided by time. That is only true if you're talking about the average speed, or you're talking about the instantaneous, but the acceleration is 0, so you don't have to worry about the acceleration. And that's the case here. Okay, so it's always safe to use the kinematic equations. Be careful with speed equals distance over time. Anyway, now we can just plug in the numbers. So delta y is 800, and the velocity is 15 meters per second, and times time. So now we get the time is equal to 53 seconds. So there's the first answer. It takes 53 seconds to get across. So now, how far downstream? That is motion in the y direction. So we'll do kinematics in the y direction, in the x direction, I'm sorry. Doing kinematics in the x direction. Delta x, v naught x, vx, ax, and time. Kind of similar to the previous situation where our acceleration is 0. Delta x is what we're trying to find. The velocity is not going to change, so it is the component of 10, and it remains at 10. And I do not know what the time is, except that I found it in the previous step. So I'll plug it in there. 53 seconds. So that allows me to use the same equation we used in the y direction, but now in the x direction. And again, this 1/2 at squared term drops out because there is no acceleration. So we'll plug in for the velocity, which is 10 meters per second, times the time, which is 53 seconds. And so we get a distance downstream of 530 meters. So there you go. That's all there is to that problem. Yep, the end.